Hello everyone. I am Nuanpan Lawson and I form the Department of Applied Statistics, Faculty of Applied Science, King Mongkut University of Technology, North Bangkok, Thailand. Today I'm going to talk about a class of population mean estimator in stratified random sampling, a case study on 5 particulate matter in the north of Thailand, and this is the joint work with Natthapat Thongsak. Thailand air pollution has become an increasing concern at present due to the amount of dust exceeding Thailand's and the World Health Organization guidelines. From this picture, you can see a nice clear sky at Doi Suthep in Chiang Mai, the province in the northern of Thailand. However, because of the burning community waste and building fire to keep warm, and forest fire contribute to small problem in Thailand, especially in the northern region. As you can see in the second picture, the smoke covered Doi Suthep in Chiang Mai, and you cannot see anything apart from the smoke. Multiple provinces in the northern of Thailand where a 24-hour average of 5 particulate matter with a diameter less than 2.5 microns, or we call PM 2.5, and 5 particulate matter with a diameter less than 10 microns on a 24-hour average exceed the standard of 50 micrograms per cubic meter, and the air quality index exceed the standard value of 100, which is classified as levels that severely affect human health. Processing air pollution data can assist in policy planning and preventing harm to life. Thailand's air pollution data have been investigated by many researchers. Carbon monoxide is used to estimate the average PM 2.5 in Dindang, Thailand, using the known prior information in simple random sampling without replacement. The best estimators with the smallest mean square error that were suggested by Lawson 2023 are based on the known median of the auxiliary variable and quartile average. The Lawson estimators exceed in saving budget and time with a small sampling fraction. The transformation technique to create combined estimators was called upon to estimate the average PM 2.5 via nitrogen dioxide in Chiang Rai under double sampling, which results in improving the performance of the combined estimator concerning the single ones. In this picture, you can see a stratified random sampling. Stratified random sampling is one of the sampling techniques that is suitable for use when the unit in the population are homogeneous within the group and heterogeneous between the group. In the technique of stratified random sampling, a population comprised of big N is subdivided into distinct subpopulations. For example, it could be divided into geographical characteristics, age group, and gender. The subpopulations are called strata. Dividing strata is useful when we want to find the size of each stratum. The samples in each stratum are selected via simple random sampling without replacement. Under stratified random sampling, there are two types of ratio estimator, a separate and combined one. So next, this is the existing estimator. The first one is the usual separate ratio estimator. For estimating the population mean is given in equation 1, and also the bias and mean square error of this estimator are shown as below, right? And next is the Taylor and Lawson 2014 estimator. Taylor and Lawson adopted ratio estimators proposed by Upadhyaya and Singh in 1999 and Singh et al. In 2004 under simple random sampling without replacement to satisfy random sampling. The Taylor and Lawson estimator are shown in equation 225, and the usual separate ratio in equation 1 and the Taylor and Lawson estimators in 225 can be rewritten in a general form as shown in equation 6, and the bias and mean square error of the estimator in a general form are shown in equation 7 and 8. And next, the proposed estimator. So in this study, a new group of separate ratio estimators is shown under stratified random sampling, inspired by the work of Cardilla and Sinti 2004 under simple random sampling. The proposed estimator is given in equation 9. As you can see that A and D are some known auxiliary information. And next, I show theoretically that how can we find the bias and mean square error of the proposed estimator. So as you can see, we use the Taylor series approximation. And here you go, these are the bias and the mean square error of the new estimator. Right, next. Here are some members of the proposed estimator as shown in table 1. As you can see that you can use any available auxiliary information. For example, the coefficient of variation, the coefficient of kurtosis, and so on. And this is the efficiency comparison to see how the proposed estimator perform. You can see from this equation here, the suggested proposed estimator is more efficient than the existing one if this equation is true, right? So next, to see how the proposed estimator perform, we will use both simulation study and also an application to real data. As you can see in this section, the simulation studies illustrate and compare the effectiveness of the suggested estimators. A population of size big N is equal to 2000 is divided into 3 strata. And we generate X and Y using a bivariate normal distribution. So these are 3 stratums and some parameters as shown here. And a sample of size N equal to 100, 200, and so on are allocated from the population of size big N using simple random sampling without replacement. And we select sample size based on proportional allocation, as you can see here using our program. And then we calculate the bias and mean square error of the estimators. And here you go, table 2 show the bias and mean square error of the estimators. As you can see that all proposed estimators perform well when compared to the existing estimator in terms of smaller bias and also mean square error. Increasing the sample size can lead to smaller bias and mean square error as well. Moreover, we use an application to add pollution data in the northern of Thailand. Northern Thailand air pollution data from 2003 to 2020 are applied to assess the effectiveness of the newest estimators. The monthly average density of nitrogen dioxide or NO2 is used as the auxiliary variable, and the PM2.5 is considered as the study variable in this study. And here the population parameters. And we consider using 8 provinces as the data, as you can see here with different parameters. And next, the result. Table 4 shows estimated values of PM2.5 and the percentage relative efficiency of the estimator. As you can see from this table, all the proposed estimator gave higher percentage relative efficiency when compared to the existing estimators. And again, as you can see from figure 1, the percentage relative efficiency of the estimator, the best estimator is the last one here that uses the benefit of coefficient of variation and the coefficient of kurtosis, right? And here the conclusion, as expected, some larger sample size lead to smaller mean square error and also smaller bias, and all the proposed estimator perform well as well. So as you can see that I propose to use some known auxiliary information. In this study, I use the coefficient of variation and also the coefficient of kurtosis. However, if you have some other available information, you can use it as well. For example, the correlation coefficient between study and auxiliary variable, or you can use the coefficient of skewness as well, and so on, quartile function, whatever. So you can see that this new estimator can be useful in estimating the study variable, and you can also apply into the real world data problem, not only the fine particulate matter, but as you may aware that nowadays that the pollution data is very important, especially in Thailand, because if some of you might not know, especially in the northern of Thailand, because the fine particulate matter is highest in the world ranking, in the last few years. So it's very bad problem, and as my daughter already said, this is very severe problem that we need to focus on this one as well. And these are the references. So thank you so much. I'm going to go back.